A computer store sells a specific type of laptop. The number of laptops sold each day is shown on the following table. Lowercase x is the potential number of laptops sold each day, whereas uppercase would have been like, this is how many laptops we sold today. The store would like to ensure that they have enough stock for all potential sales of laptops. Calculate the expected value of the demand and the standard deviation. So the really cool thing about math is that what we can do is we can actually just plug in these probabilities into your calculator into the lists and spreadsheets page just as the probabilities. Because if we multiplied all of these probabilities by the total number of laptops sold, it would end up giving us a number that we would be multiplying all of these guys by the same number, which means that the relationship of them would all stay the same. And so that's why we can plug in the probabilities, is because the relationship of these numbers together is still consistent, whether we multiplied all these numbers by 100 or a million or multiplied them all by 3.2. The relationship of them all would stay the same because we multiplied them all by the same number. And so I could have multiplied all of these by 2 and then put all of that into here, even though it's not the probability, that relationship still holds. And so as a result, what you end up getting, that weight of each of these numbers, right? This will still have the number 1 will still have the highest weight out of all of these in correspondence to the other ones. I hope that made sense. But the reason why we can just plug in the probabilities is because that relationship stays the same. Once you plug those all in, we go to menu, statistics, stat calculations. We're doing one variable, statistics. And our probability is frequency. It's relative frequency, but that's what we're going to put here, is that the A list is where our X values are. Our frequency list is the B list, or whether you have TI-84 or not, might be slightly different, but you can hopefully by now make a connection of what you need to do on your calculator. So then go ahead and calculate this out. Oops, there we go. Your expected value is your average. So while it's X bar here, what we're going to do is represent it by mu, or E of X equals 1.9. And then it also asks for our standard deviation. What's the standard deviation of what's going to possibly happen? And our standard deviation is in the place it always is, 1.2. Since it's a 6 after that 7 is going to round up to 8. Which means I should expect to have about 2 laptops sold per day, maybe 1, maybe 3, but that's kind of the information that you can take from there. About 2, because this is about 2. 1.28 is our standard deviation, which means like, okay, the average of the distance of these values from the mean is telling me that, like, okay, I'll normally sell 2, but maybe subtract about 1 or add about 1, and that'll be like, okay, so maybe like 1, 2, or 3 per day, which makes sense. All right, hopefully this is all feeling pretty familiar and not too crazy. I think the only crazy part about this lesson in particular is all of the new vocab that's representing the same ideas as what we've been doing before. So expected value instead of mean, using mu instead of the X bar. The statistical abstract of countries is usually published annually. One of the questions asks the country's household to report the number of persons living in the household. The following table summarizes the data for a certain country. So the number of households in millions and number of people who live in that household. We want to develop a probability distribution of the random variable defined as the number of person per household. So it's just saying develop a probability distribution for this guy. I am going to be lazy. And I'm going to just extend this table. Is it lazy or is it efficient? I'm going to say efficient. And I'm going to put my PMF here next to those values. So it already tells me what the total is here. Remember that developing a probability distribution is just, it doesn't tell us to do it by table. It doesn't tell us to do it by graph. So we can do it either way. Normally it's by table, because you have to do a table first before you can do a graph. So all we're really looking for here is that relative frequency value. So I just need to take each of all of these and find the probability that that occurs out of the total amount. So divide it by 116. So 31.1 divided by 16 is going to be 0.268. I'm going to go ahead and ask you a question that's going to pop up soon about the probability distribution for the rest of these guys. So go ahead and fill in the table that you see now. All right, so dividing them all out, we should have gotten 0.333, 0.162, 0.140, 0.062, 0.023, 0.012. If you add those up, they should all add to 1. Put a little space there. Okay. We're going to find the probability that a randomly chosen household has 4 or more persons. So that means the probability of 4 plus the probability of 5, probability of 6, or the probability of 7 or more. When we start to actually calculate this, we actually start to deal with this as just 7. Is it accurate? No, but we're saying, okay, the number 7 is going to represent 7 or more. All right, so all we need to do is add each of those probabilities, probability of 4, 5, 6, and 7 or more. Go ahead and find that for me. You should have gotten 0.237. Again, nothing groundbreaking, nothing huge. We're just getting used to the vocabulary here today. We're going to calculate the expected value and the standard deviation and consider the last class to be 7. So here it's saying, go ahead and type in 7 for this guy instead of 7 or more into your calculator. I think you don't need me to hold your hand on this, so go ahead and just calculate that and tell me what you get. For your expected value, you should have gotten 2.512. For your standard deviation, 1.398. I decided to do 4 significant figures because this was going to be annoying, so I just wanted to do 4 instead. Okay, last problem, example 6. What is the probability distribution of the discrete random variable x that counts the number of heads in 4 flips of a coin? These types of questions, I think, are the scariest types of questions for me. Like if I was trying to think about if I was a student, I would be nervous about these types of questions, I think, because it doesn't seem very evident at first what the question is asking. It's really hard to understand what the question is asking. I don't see a lot of numbers. I'm not given a table of values. And to find a probability distribution, that vocab is still really new to me. And so I might be freaking out a little bit about this question. A probability distribution means that we need to find frequency, and then from frequency we can find that relative frequency or divide it by the total number of occurrences. And what we're looking at here is how many times heads show up when we flip 4 coins. And it could be 1 flip, a second flip, a third, and then a fourth. But the idea is that we have 4 results, and it could be head, 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 or head, tail, head, head, or head, tail, tail, head, right? It could be a bunch of different options, and we're trying to count how many times a head occurs. So our x value could be 0, right? We could have 0 heads show up. Our x value could be 1. We could have only 1 head show up. 2, 3, or 4. So if 4 heads showed up, that meant that it would be H, 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 right? All 4 of those tosses turned up heads, and that would be 1 occurrence that had happened. If 0 heads showed up, that meant that it was all tails. Okay, so then if 1 head shows up, that means that maybe that head is here at the beginning and the rest are tails. But in these instances, hopefully as we're starting to realize or remember, the occurrence in the instance in which the head occurs is important. It's viable to look at. So it could be first, but also the head could be second. And that is a different occurrence. It could be third, or it could be fourth. All of those are different occurrences, but all of those are all of the occurrences in which head shows up 1. It's the same situation for when heads shows up 3 times. That means that tails only showed up once. So the tail could be first, it could be second, it could be third, or fourth. The last one's a little bit trickier to kind of visualize the manipulation to figure out how all of the different instances that it could occur. With 2 and 2, there's a lot of different ways. So it could be 2 tails and then 2 heads. Or it could be 2 heads and then 2 tails. Or it could be a tail and then a head and then a tail and then a head. And then I like to think of solidifying or keeping these first 2 and then flipping the last 2 and how that's kind of finishing the thought process of this guy. It could be tail, oops, tail, head, head, tail. Or we could do head, tail, head, tail. Or again, that same thought process as before, head, tail, tail, head. And those are all of the occurrences of when only 2 heads show up. So sometimes for me, I like to visually write it out like this. I think it's hard to understand what the probability distribution is if you don't understand how all the possible outcomes or all the possibilities of doing it this way. So if I were to break this down, first of all, just into number of heads as a table, 0, 1, 2, 3, 4. And I just wanted to calculate their frequency. 0 heads would be a frequency of 1. 4 heads would be a frequency of 1. A frequency of 1 and 3, or sorry, number of heads being 1 and number of heads being 3 have the same number of frequency. It's 4. And then 2 is 1, 2, 3, 4, 5, 6 different frequencies, 6 different occurrences. That total is 16 if you add it up. So then if I want to go ahead and find my probability distribution, my P of X, I go ahead and divide each of these guys by 16. So go ahead and tell me what these probabilities are. 1 divided by 16 is 0.0625, which means that's going to be this guy down here. 4 divided by 16 is a fourth, or 0.25. And then 6 divided by 16 is 0.375. Great way to check is that all of those probabilities should add up to 1. So that's a great way to make sure that you've done all of your calculations correctly. I think that's everything. Our next lessons are going to be talking about different types of distributions that can occur. So we talked about how to find probability distribution, about things that like calculations we can do with probability distributions, and now we're talking about what types of probability distributions can you have. You have a normally distributed one, as well as a binomial distribution of one. All right, good job.